Hi everyone, this is Sherry Sahebi, data mining class, and we are going to talk about logistic regression today. So what is logistic regression? It is a way to classify our data. So let's see what classification is. So far, what we have learned was linear regression and kernel regression, in which what we had was that so in linear, for example, regression, what we had was that our data set, D, it was pairs of vectors xi's and a yi. And this yi was a numeric value. And we wanted to predict yi's to be able to, like, using the linear regression or the kernel regression. So we had these pairs of vectors xi's which had different independent attributes in them. And then yi was our response variable and or our dependent variable, right? So we had independent variables in xi's and we had a numeric response variable that we would like, we wanted to predict. But in classification, our task is a little bit different. And the difference is that instead of having numeric response variables, what we have is categorical response variables. So again, our data is having these pairs of vectors of independent variables or attributes. And then we have these categorical variables, yi's. Now, we don't call them response variables anymore. What we call them are class labels in this case. So this is, we call them class labels. Okay. xi's, we assume for this, for now, that xi's are numeric. So we have d-dimensional xi's. So they belong to R to the d. Now, the yi's, we said that they are categorical, right? And they are class labels. What can we give as an example of such a task that you are given some numeric attributes and you are expected to predict some class label or a categorical label for your data with numerical attributes? One example would be that suppose that you are given the height and weight and number of legs for animals, and these are your attributes for your xi's, and your predicted class, or the class that you would like to predict, or the attribute that you would like to predict, the class label is the type of that animal. So, for example, you are given the height, weight, and number of legs for n animals, and your class label is going to be if it is a cat, if it is a dog, or if it is a hen, for example, right? So depending on these different numeric attributes, we would like to classify our data points into one of these three classes. It is categorical because it's either a hen, a cat, or a dog, right? That is basically what we would like to do with classification. There are other examples for classification also. So suppose that you are given a medical data set with some attributes, xi's, that your data point xi's are the fever of the person that you are looking at, or the fever in terms of body temperature, or you are given some lab test results and they have numbers in them, like number of blood cells and all of that, and you would like to classify this patient, each patient, as if they have a flu, if they have a cold, or if they are having COVID-19 virus. So these categories, flu, cold, COVID-19, are your class labels that you would like to predict. Okay. So basically, our response variable here is a categorical value, but your input, we assume for now that our input is numeric. Now, when we have we have seen our examples that we have 3 different categories or classes in them, right? Cat, dog, hen, or flu, cold, COVID. We can have as many as we want. So we can have 10 classes, 100 classes. We can have as many classes as we want. But in the case that we have 2 classes only, we call that a binary classification. So for example, suppose that you are given a data set and you just want to figure out if the animals in that data set are cats versus dogs. So you only have 2 classes, so you do have a binary classification task at that point. When you have a binary classification task, usually what we do is that instead of yi being cat or dog, what we do is that we encode these classes, these 2 classes, into 2 different classes. So for example, we say if it is a cat, we say yi is 0. If it is a dog, we say yi is 1. So in case of binary classification, what we have is an encoding, a numeric encoding for yi, and yi is basically going to be either 0 or 1. And we know ourselves that what is class 0 and what is class 1. Okay. Now, because we always, you remember from linear regression that we always augmented our input data. So if our input data was d-dimensional, because we didn't want to include the bias term in our calculations as a separate thing, we wanted to add bias to the vector, parameter vector w, we always added a vector ones at the end of our data points, right? So our data d was like this. So it was x0, x1, attribute xt, and x0 was always 1. So this was our augmented data point. So this is data point x1, data point x2, etc., data point xn. And then we had this variable y before, right? Now here, in the case of binary classification, y can be 0 or 1, right? So because we are working with augmented data, we always assume that our xi's are in the d+1 dimensional space, augmentation for 1 additional x0. Okay. Now that we have these 2 binary variables, what we can look at is now as yi is that we can look at the probability mass function for the class label or the response variable here instead of the value that it can take itself, because it can just take 2 values. It's either 0 or 1, right? So what we are interested in is that if I am given a data point xi, what is the probability that my class label is 0, and what is the probability that my class label is 1? So what I'm looking at is the probability that yi is 1 given that my xi is the xi that is given to me. And also the probability that my yi is 0 given that I have this input xi. So if I define both of these, if I find both of these, because yi can be either 1 or 0, I'm having my full probability mass function, right? Let's, just for the sake of simplicity, let's assume that this is equal to a value pi, so pi of xi. Okay, we all know that a property of probability mass functions is that the sum of probabilities should be equal to 1. So basically, the probability that y is 1 given xi plus the probability that y is 0 given xi should be equal to 1, right? That's the property of a probability. So if I have a probability of y is equal to 1, which is equal to pi xi, then the probability of y equals to 0, it's going to be 1 minus pi xi, right? Okay. And what our goal is that this pi, as you can see, it's a function of xi, right? The probability that a specific animal is a cat, it depends, according to our data set, it depends on its weight and its height, right? So it's a function of height and weight. So it's a function of xi. So this pi is a function of xi, and when we want to find a good classifier, what we are trying to do is to find this function pi. Finding a function that if we apply it to xi, it can give us the probabilities of class labels accurately. All right. So our goal is to infer this pi. Okay. Now, some of you may say that, oh, okay, why aren't we applying linear regression directly and find these yi's according to linear regression? The problem with that is that when you apply linear regression on your data, what you are going to get is a numeric value, right? So your prediction is a numeric value. It's not just a binary 0 or 1. So your prediction can be 0.45, it can be 1.2, or anything like that. Now, after you do this prediction, after you find this yi out of linear regression, then now you have to decide if 0.45 means a 0 label or a 1 label, if 1.2 means a 0 label or a 1 label. So that makes things a little bit difficult because it's going to be very ad hoc. So that's why what we are doing is looking at these probabilities mass functions. So we are looking at the probability that yi is equal to 1. And that is going to be way more interpretable and easier. Okay, and as you can see, also in the case of binary classification that we have here, it looks like a Bernoulli random variable, the probability of yi being equal to 1 or 0, right? So our goal is basically inferring the parameter of that Bernoulli random variable according to xi. This is the definition of binary logistic regression task. Okay. Well, binary classification task. We didn't get to logistic regression part of it yet, but we are going to go there now. Okay, so far we said that we want to look for a pi of xi, a function pi that can give us a good prediction of the class label. Now, we have to find a model for this pi, right? So we can, for example, find some function families and say that, okay, I want this pi to follow these function families. Now that we are looking at binary logistic regression and we have learned about linear regression and kernel regression, what we can do is that we can pick the pi to be of a regression kind of family, right? A regression kind of function. So the first thing that comes to our mind is that, okay, let's say that pi of xi is a regression function. So I can say pi of xi is equal to w transpose xi. And then I'm going to find the w's that does the job, and we are going to be okay with it. But the problem of doing this is what? We know that pi of xi, the thing that we are looking for, is a probability, right? And you remember that the probability functions, the probability mass functions, they have these properties that they have to be between 0 and 1, right? And also, the summation of pi for all the different possibilities of yi should be equal to 1. Okay. But if I do this, if I do this W transpose Xi, it is not between 0 and 1. What it is it is between negative infinity. It can be between negative infinity and positive infinity, right? So if I just use W transpose Xi, I can get any values between minus infinity and plus infinity. So what should we do that if I want to still stick to this simple regression kind of function? It is a very basic function, right? But then I want to get a probability mass function out of it. What should I do? I cannot just do W transpose Xi. So what we are going to do is that we are going to pass this W transpose Xi value through another function, that this function is going to restrict the value to be between 0 and 1 for me. Okay. What kind of a function can do that? Well, there are different kinds of functions that can do that, but what we are going to choose for the logistic regression is a sigmoid function. Okay, what is a sigmoid function? The sigmoid function, it's usually called sigma, but because we are using sigma for the variance and standard deviation and all, we are going to use theta here in this course instead of sigma for it. So the sigmoid function, what it does is, suppose that we are calculating the sigmoid of a variable z. Now z can be between minus infinity and infinity. The value of theta for z is going to be 1 over 1 plus e to the minus c. This is the definition of sigmoid function. Okay, so how does it work? How does it make your number z to go between 0 and 1? Let's look at the extremes of z here. So if my z is equal to 0, what do I get? Theta of z is equal to 1 over 1 plus e to the 0. This is 1, so it's going to be 1 over 2. It's going to be equal to 0.5. Okay, so if z is 0, we get 0.5 out of sigmoid. If z is minus infinity, let's see what happens. So theta of z is going to be 1 over 1 plus e to negative of minus infinity, which would be infinity, right? Okay, e to infinite, it's infinite, so we are going to have 1 over infinity, which is going to be 0, right? So if I am at negative infinity, the sigmoid of my negative infinity is going to be equal to 0. What if I'm at plus infinity? Then my theta z is going to be 1 over 1 plus e to minus infinity. Okay, this guy is going to 0, so I'm going to get 1 over 1, which is 1. So if I am giving a number plus infinity to this function, then I'm going to get a value of 1 out of it. You can see that from negative infinity, that the value of theta is going to be 0, to positive infinity, the value of theta is going to be 1. And in between, we have theta of 0 being equal to 0.5. Okay, so basically, we have seen that with some samples, that how it is going to be bound, the value of theta of z is going to be bound between 0 and 1. So now let's look at actually the sigmoid function. and see how it looks like. So if this is our z, this is our theta of z, we have seen that at z equal to 0, it's 0.5. At z infinity, it's going to be 1. And at 0 negative infinity, it's going to be 0, right? So it's approaching 1 and approaching 0 in these two extremes. Now, the way that it connects these three values to each other, you can see that this is an exponential function in the denominator. So basically, if you plot this function, you are going to get something like this. It's, yeah. Okay, so this is going to be our sigmoid function. So any value that I give to it at any point, it is going to restrict it between 0 and 1. So what we can say is that, okay, we are not going to have theta of xi to be equal to W transpose xi itself, because we have this restriction on the probability values, but instead we can say that theta, the pi of xi, is equal to the sigmoid over the value W transpose xi. So I still have this linear part of my function, my model, but I apply a sigmoid function on top of that just to get everything between 0 and 1. Okay. So basically, this means that my pi of xi is going to be equal to 1 over 1 plus e to the minus W transpose xi. Okay. Now, okay, so what we have done now is that we have translated finding a pi of xi. You remember that here we said that this is our unknown function, and we would like to find this unknown function, right? So we have translated finding this unknown function pi of xi to finding the parameter values of W, right? So now we have the unknown weight vector, W, right? That is R to the D plus 1 because it includes bias term. Okay, so now our goal is to find W. It's a little bit simpler because pi of xi could have been any function, but here we have defined the type of function that we are looking for, right? And we now are just looking for the parameters of that function. Okay. Again, remember that W transpose xi is a scalar value. What is W transpose xi? It is W0 xi0, which is 1 always, plus W1 xi1 plus W2 xi2 plus etc. WD xid. So this is a scalar. We apply sigmoid on top of that, and we are going to get a value between 0 and 1. Okay. Another interesting property that the sigmoid function has is that if we calculate theta of minus z, it is going to be equal to 1 minus theta of z. Okay, so you can prove that at home if you like. So, all right. So far, we have defined our Bayesian logistic regression problem. What is our logistic logistic regression problem? What is the binary logistic regression problem? We would like to find these W's that can best fit our data. Okay, so if I am given an input vector xi, applying this logistic regression formulation, I can find the probability that this data point xi belongs to class label 1 or the class label 0. All right. Okay, so yeah, again, this is the form of a logistic function, and so basically that's what you can see. And these are the properties of logistic function that we went over. Okay, so what we have, now let's look at our classification problem. So what we have is that so far we said that pi of xi, we set pi of xi to be 1 over 1 plus e to the minus w transpose xi. Okay, so let's go back to our probability function and see what we have. So what we had as our probability mass function was this. We said if we are looking at probability of yi is equal to 1 given xi, it is going to be equal to pi of xi, which is 1 over 1 plus e minus w transpose xi. And whenever yi is equal to 0, we have this probability of yi is equal to 0 given xi is 1 minus pi of xi, right? Which is basically pi of negative. So 1 over 1 plus e to W transpose xi. Okay. Or in other words, we can basically write it 1 minus p of W transpose xi. Doesn't matter. So all of them are equivalent, right? Okay, so our probability function, so this is probability of yi given xi. Okay. So our probability function is defined in this way that is kind of discrete, right? If I want yi is equal to 1, I should look at this top one. If I want yi is equal to 0, I should look at this bottom one. Is there a way that I can combine these two and have just one formulation, one nice formulation for my probability of yi is equal to xi? Let's look at it. So we said if yi is equal to 1, it's going to be equal to probability of xi, right? And if yi is equal to 0, it's 1 minus probability of xi. So if I look at this function, I would say probability of xi to the power of yi. If yi is equal to 1, this term is going to be equal to pi of xi. If yi is equal to 0, this is just going to be 1, right? So this is going to be, if yi is equal to 1, it's going to be pi of xi. If yi is equal to 0, this is going to be 1. Now, let's look at another term. What if I look at this one? 1 minus pi of xi to the power of 1 minus yi. What is it going to be? If my yi here is equal to 1, 1 minus yi is going to be 0, so this whole term is going to be equal to 1. If yi is equal to 0, though, then this is going to be 1 minus pi of xi to 1, so it's going to be equal to 1 minus pi of xi, right? So if I look at the multiplication of these two terms, what happens? If I look at this whole thing together, then I get if yi is equal to 1, it's going to be equal to pi xi multiplied by 1. It's going to be pi xi. If yi is equal to 0, it's going to be equal to 1 multiplied by 1 minus pi xi, so it's going to be 1 minus pi xi. Nice. This is equivalent to the probability of yi given xi that I had before, right? There also, if yi was 1, we got pi of xi. If yi was 0, we got 1 minus pi of xi, right? So basically, this is a very nice way to rewrite our probability of yi given xi only in one line, right? Okay. So now we got a formulation for the probability of yi given xi. So now I have probability of yi given xi is equal to pi xi to yi multiplied by 1 minus pi xi to 1 minus yi. Nice. That is a nice formulation that I have here. Now, okay, so if I have this, then what can I say about all of my data points? So this is for one data point, right? yi and xi. What can I say about all the yi's that are out there, or all the xi's that are out there? So if I rewrite this for probability of y equals to 1 given x1, probability of y equals to 2 given x2, etc., that would give me the probabilities for the for each data point, right? So I have this for x1, for x2, I have this. And for xn, sorry, because we have n data points, I have this. Okay. So if I want to calculate the joint probability over all of my data set, including y1, y2, x1, x2, etc., all n data points that I have, how should I do that? So you know that the joint probability of two different variables is equal to the multiplication of each of their probabilities if the two probabilities are independent of each other, right? Also, in many cases in data mining, what we do is that we assume that our data points in the data set are independent of each other, right? They are, we have this IID assumption that has like they are independent of each other and they are identically distributed from the same distribution. So basically the probability for, or the likelihood for the whole data set that we have, which has all yi's and xi's, is going to be multiplication of all of these probabilities. It's going to be probability of y1 given x1 multiplied by probability of y2 given x2, etc., by probability of yn given xn. And we can write it compactly as this joint multiplication of I going equal to 1 to n probability of yi xi. So this is going to give us the likelihood of our data. So if I have these pi i's, then what is the likelihood that I see these data sets? So if I see this xi, I see that yi. If I see this xi, I see that other yi, etc., etc. Okay. That's one thing that we are going to work with very soon. But also, let's look at this probabilities in another sense also. So when we have this pi, when we have this binary classification, what we can look at to interpret the values that we get for probability of yi given xi, we can look at a value called log odds ratio to see what happens if we have 1 unit change in xi. Okay, what do we mean? So we said the probability of yi given xi is equal to this. So pi of xi to the yi, which is basically theta of w transpose xi to yi multiplied by 1 minus theta of w transpose xi to 1 minus yi, right? This is the same formulation that we have seen before. Now, to see if we change xi's, like if we see a 1 unit change in our input, so one of the xi's, what happens between the probability of yi that we are getting? How much does it go closer to yi being equal to 1 versus it goes closer to yi being equal to 0? What we look at is we look at the probability of yi equals to 1 given xi, this ratio, over probability of yi equals to 0 given xi. Okay, this is called odds ratio. So it's the ratio between the odds, right? So what is it equal to? That is going to be equal to, because if yi is equal to 1, we are going to have theta of w transpose xi, right, as the value of p. If yi is equal to 0, it's going to be 1 minus theta of w transpose xi, right? Which is basically equal to, we have seen that, it's equal to w transpose xi theta over theta of negative w transpose xi, right? So 1 minus theta of z is equal to theta of minus z. Okay, so what I can do is that I can say this is equal to theta of w transpose xi multiplied by actually I can look at this as this 1 over 1 plus e to the w transpose xi. I can do that. I can multiply both sides with the same thing, right? So I can multiply both sides, like the numerator and denominator, with the same value of, sorry, this is plus, yes, the same value of e to the negative w transpose xi. So I'm going to get this 2 minus 1, and then over e to the w transpose xi plus 1. Actually, let me show you how we get there. It may be easier. So, okay. So theta of w transpose xi is 1 over 1 plus e to negative W transpose xi, right? And theta of W transpose minus W transpose xi is going to be equal to 1 over 1 plus e to the W transpose xi, but minus 1 because it is in the denominator, right? Now, if I multiply the numerator and denominator of this one to e to the W transpose xi. Okay, what do I get? I get e to the W transpose xi in the numerator, and then in the denominator, I get e to W transpose xi, because it's multiplied by 1, plus e to W transpose xi multiplied by negative W transpose xi, which is basically, it's going to be this minus that, which is going to be e to the 0, which is going to be equal to 1, right? Multiplied by 1 over 1 plus e W transpose xi negative 1. So this whole thing is going to be equal to e W transpose xi and e W transpose xi plus 1, right? Multiplied by, now this is basically equal to 1 plus e W transpose xi, right? Because if we make this minus 1 to the minus 1, it's you're going to swap the numerator and denominator. Okay, so these two will cancel out, and this will be equal to e to W transpose xi. Okay, so what have we done? What we have done is that we are looking at the probability of yi being equal to 1 over the probability of yi being equal to 0, and we concluded that it's equal to e to the W transpose xi. So what does it mean? If I take the logarithm of both sides, it says logarithm of odds ratio here is going to be equal to W transpose xi, which is the summation of I equals to 0 to d wi, or let's say j, wj xij, right? So what it means is that if I change my xi one unit value, so instead of xi, I have xi, instead of xij, I have xij plus 1, the change that I see in terms of probability of yi over probability of 0i is going to be linear with respect to w, and that's the change that I see in terms of the log, right? So one unit change in xi is going to affect the log odds ratio linearly with respect to w. Okay, so this log odds ratio function is also the logit function that you see here. Okay. So that is basically going to make us make things a little bit more interpretable, because then we would understand what happens if I change one of my attributes one unit, then how much I'm going to get closer to probability of y equals to 1, or how much am I going to get closer to class label 1, and how much I'm going to get closer to class label 0. Basically, that's what we are having here. Okay, so that's just for interpretation. Okay, so we have seen so far, we have defined the problem of binary logistic regression. We said that we would like to find this unknown function pi of xi that represents the probability of class label being equal to 1 given my data point xi. And then we said, okay, in binary logistic regression, we define the the pi of xi function to be a sigmoid of W transpose Xi, which is basically a logistic regression function, right? So we have W transpose Xi being similar to our linear regression, but we apply sigmoid on top of that to be able to get probability out of it. And now the problem of finding a good function pi of xi is translated into finding a good set of parameters for the weight vector w from our dataset. And then we also calculated a nice formulation for a compact formulation for probability of xi given yi given xi instead of having two different separate parts. And also we calculated what is the likelihood of our data points. Now, let's see how we can get to find a good W. So finding the parameters of our model. You remember from linear regression that when we wanted to find a good W, good set of parameters for the model, we defined an error function. And then we said, okay, our goal is to minimize that error function. And that's how we took the derivative of the error function with respect to W, and we found a good W there. But here, we are looking at the probabilities, right? We are looking at the probabilities of our classes to happen given our data points. And also we are having this likelihood of our data. So the likelihood of our data that we have defined here this is something that we can use instead of the error function to find the values of W. How? We can say that the likelihood of D is actually, it's given the parameters W, right? Because when we are calculating the likelihood, we are saying that it's equal to I equals to 1 to n probability of yi given xi to yi multiplied by 1 minus probability of yi given xi. Oh, sorry, that's equal to this, which is equal to, so now if I rewrite the probability of yi given xi, it's going to be I equals to 1 to n. We have it here. We have defined the probability of yi given xi here. It's pi of xi to yi multiplied by 1 minus pi of xi to 1 minus yi, right? Which is equal to, because we have defined the pi's, right? I equals to 1 to n theta of W transpose xi to yi multiplied by 1 minus theta of W transpose xi to 1 minus yi. So you can see that the likelihood of our data, it depends on the W's because we have the parameter W here. Our xi is known, it's coming from our data. Our yi is known, it's coming from our data because our data was basically we had these xi's and we had these yi's, right? This was our data. So these are coming from our data, but we don't know the W's. So our unknown parameters are the W's. And the likelihood of our data given our model, given our W can be defined then. right? So basically, it's as if we are saying that this is given. It's as if I want to rewrite this whole thing, I can write it like this. I can say the likelihood of D given W is going to be equal to the probabilities of Yi, all the Yi's that I'm seeing given Xi's and W's, right? This multiplication. Or actually we can assume that Xi is already there and simply write the probability of Yi given W. Okay. So what do we want from W's now that I have defined the likelihood of my data in terms of W? We want to find the W's such that if I calculate the likelihood of my data with those W's, that likelihood is as high as possible, right? I want the probability that I see each of my data points with that W to be very high because I have already seen these data points. So I know that they are out there. So if I have a W that that tells me, oh, the probability, the likelihood that you see this data set that you have is very low, I don't trust that W, right? Because I have seen that data. I know that it exists. So I am looking for a W that tells me, hey, yes, the likelihood that we see this data that you have is really high. And then I can trust that W, right? So basically our goal here is to find the parameters W such that the likelihood, the data likelihood, the likelihood of the data sets that I have observed, data likelihood is maximized, right? So now I have an objective function then. So what I'm trying to do right now is, if I translate it, is to find the W that maximizes L of D given W for me. Right? Okay, now that I have this objective function, similar to when we wanted to solve this problem for linear regression, what we can say is that if I do have a function, so suppose that I have a function and it's like this, and I'm looking for a, let's make it simpler, and it's like this, and I'm looking for a W, this is my W, and this is my likelihood function, L of W. Now, if I'm looking for a W that maximizes this likelihood function, what do? If it's a simple function like this, we would say we take the derivative of this function L of W with respect to W, and we set it to 0. Here is the point that the derivative is equal to 0, and also it's the peak, and so this is going to be my W, best W or W star that is going to give me to maximize L of W, right? Okay, so what happens if we want to do that? Let's look at L of W. This is the likelihood function that we are working with. And so if I want to take the derivative of this thing with respect to W, you can see that there are so many multiplications there, right? We have the multiplication over all of our data points and then another multiplication inside this. So I have to apply the chain rule so many times, and it's going to be a very complicated derivative. So it's not that easy to work with that. What should I do? What we can do, and what we usually people do in when they want to optimize a likelihood function, is that instead of differentiating the likelihood function itself, we try to maximize the logarithm of the likelihood function. So instead of maximizing L of W directly, instead, because this is difficult, what I do is that I will try to maximize the logarithm of L of W. So I would find W that maximizes the logarithm of it. Why does this work? So first of all, because the logarithm is a monotonic function. So if I find a W that maximizes L of W, that same W is going to also maximize the logarithm of L of W. Okay, so that's a good thing. So if I can find a W that maximizes this whole thing, it's the same as a W that maximizes this thing. And another good thing that happens if I take the logarithm is that all of these multiplications are going to be a summation instead. And working with summations is way easier when you want to take the derivative, right? So what we do is that now I want to calculate logarithm of L of W. So I would say, let's look at ln of L of W. I just dropped the D to things easier. We just look at LW. So that is going to be equal to, this outer multiplication is going to be changed into a summation, right? So instead of multiplication from I equal to 1 to n, I'm going to have a summation of I equals to 1 to n, and the logarithm can go inside then ln of, we have it there, theta of W transpose xi 2yi dot 1 minus theta of W transpose xi to 1 minus yi. Okay, now again, I have the multiplication inside, and if I take ln inside, that is going to be equal to I equals to 1 to n, ln of this first term, theta W transpose xi to yi, plus ln of the second term, 1 minus theta W transpose xi to 1 minus yi. Okay, and then if I take the ln of this one, because it's theta 2 yi, it's going to be equal to I equals to 1 to n yi multiplied by ln of theta W transpose xi plus 1 minus yi ln of 1 minus theta W transpose xi. These are all vectors. Okay. All right, so now we do have a logarithm of likelihood function. So this is log likelihood. And we can try to find a W that maximizes our log likelihood, right? So then we can find the W. Again, You remember that when we were looking at linear regression, what we had was an error function that we wanted to minimize. Here, because we are working with probabilities and likelihood, we want to maximize it according to the data, right? But what happens if I want to look at it in terms of error, like similar to linear regression? So let's see what happens. If I want to maximize my logarithm of likelihood, so I want to find a W that maximize ln of L of W for me, if I want to rewrite this as a minimization problem, what can I do? I can say the W that maximizes this guy is equivalent to the W that minimizes the negative of that, right? Function. So maximizing log likelihood is equivalent to minimizing negative of log likelihood. So the negative of log likelihood, we can say it can work as an error function for us. It's similar to an error function that we can minimize. If you would really like to think of it as an error function. Okay, and that error function has a name, and that is called cross entropy. And if you actually want to see how it will look like, it's very simple. It's very similar to log likelihood. The only difference is that it is negative. So inside the logarithms, we can just say instead of logarithm of W transpose Xi, we can have the logarithm of 1 over theta of W transpose Xi, which is going to be negative of the original one. Okay, so this is the cross entropy function, just so that you have an interpretation of error minimization instead of maximum likelihood estimation. Okay, now let's go back to our optimization problem, and let's see what we can do to find W. Okay, so far, what do we have? We would like to find the W that maximizes ln of LW, which is equal to I equals to 1 to n yi ln of theta W transpose Xi plus 1 minus yi ln 1 minus theta W transpose Xi. So we want to do that. So as we said there, if we do have, suppose that we only have one parameter W, so we are in one-dimensional space, and what we usually do is that we take the gradient, we set it to 0, and we find W star. But still, we have a problem. What is that problem? If you look at this W, although the form of this L function is way nicer than like the log likelihood function is way nicer than the likelihood function itself, because it's summation instead of multiplication. But still, if I take the derivative of ln of L of W with respect to W, and then set it to 0, I want to set it to 0, the problem is that this derivative is not going to give me a closed form solution. So what do I mean by that? You remember that in linear regression, when we did that and we set this derivative to 0, we could actually solve for W in one shot and say, okay, W is equal to X transpose X, inverse of X transpose X multiplied by X transpose Y, or something like that, right? But here, if I want to do that, I won't be able to find this closed form solution. So instead, what we are going to do is that we are going to solve this problem step by step by taking the partial derivatives or gradients, and we are going to use an algorithm that is called gradient descent or gradient ascent, actually, in this case, to get to the W that we are looking for. So how does this problem, how does this algorithm work? Again, suppose that, suppose that I have a one-dimensional space. So I just have one W, like W1, for example. And this is my ln of LW function that I want to maximize. And now suppose that it looks like this, something like this. And I want to find this W star that maximizes this, the value of L. Okay. Well, I am looking at this function. I know where W star is, but in practice, when you are trying to do this, you cannot really see it, right? So what we do is that we start at a random value for W. So I would say, suppose that I pick a random value for W, let's call it W0. And then I calculate the value for ln of LW for that W. Okay. Now, in the next step, what I would like to do is to update my W0 such that I get a better or more value for ln of LW in the next step. So basically, if I want to do that, if I want to change W so that this value of this function is more, I know, like just if we look at this diagram, we know that we should go to the right? So for example, my W1, in the new W that I'm going to have, it should be to the right of this W0, because if I go to the right, the value for my function is going to increase. But then if I go to left, the value is going to decrease. So I won't go to the left. So I don't want to go to the left. I have to go to the right. But we see this, and that's why we are concluding that we have to go to the right. In reality, when we are trying to optimize for this function, we don't observe the function. So how do we know if we have to go to the right or we have to go to the left? We have to go to the right in this case, because if I look at this function, if I look at the slope of my function at this point W, I can see that it's a positive slope, right? It's a positive slope. So if I go to the right, if I increase the value of W, I'm going to get a higher value for f of W also, the value of the function. So what is this slope? This is the gradient. This is equivalent to the gradient of my function at point W0. So if the gradient is positive, then I will go towards the direction of gradient. So I will go to the right, to the positive, more positive side, and then I will get more values of function. But if I am at a point, like suppose that at this point, suppose that my W0 is here at some point, and I take the gradient, and the slope is negative here, right? If my gradient is negative, then I should go to more negative values of W. I should go to the left of W to be able to get higher values for f of W, right? So basically, it means that I have to move towards the direction of gradient at each step to get to W's with higher ln of LW values, right? So at this point, I take the gradient, I see it's positive, I move to W1. Then at W1 again, I take the derivative, I see it's positive, I move towards the more positive, I move to W2. Again, at W2, I get the derivative, I see it's positive, and then I move a little bit more. And for example, when I get to W star, which is my actual best value for W, the gradient is going to be equal to 0. And then I know that, oh, okay, so I am at this peak. So I'm good. That's how the gradient descent, gradient ascent algorithm works. It's gradient ascent because we are trying to maximize the function. If we were trying to minimize the value of the function, it would have been gradient descent because we were going down. But here in gradient ascent, we are going up the hill. So we have to move in the direction of the gradient. So what we do is that at each step, we take the gradient. We first start with a random value or an initial value for W. We take the gradient and we move towards the gradient direction at each step. We do it step by step and until we get to a good value for our W. And we can see what that kind of a stopping criterion is. So basically, this is what we are going to do. We start at some initial value for W, we call it W0. And at each step, we move in the direction of gradient or the steepest ascent. So at each step, at each time t plus 1, we set the W for t plus 1 to be equal to the W for t, so the previous step, plus the gradient of our function at the previous step. And also we have this step size or learning rate to tell us how big of a jump we should take. So for example, here, moving from W0 to W1, I do calculate the gradient. I know that I have to move towards the right-hand side direction, but how big of a jump I should take? Should I take this big or should I take this big? You know, that is defined by learning rate or step size. And that is going to be defined by us. Usually what people do is that the best way to do it is to start with larger values of learning rate. And then as we go forward, we make it smaller and smaller so that it gets more precise. If it's too large, we are going to have a zigzag problem. So if it's too large, what happens is that we are going to jump from here to this side and then from this side to this side. So we are going from one side of the peak to the other side of the peak without really getting into the peak if it's too large. But then if it's too small, then we are going to take too many very, very baby steps and it takes forever for us to really get to the best W. So it should be a decent value. And usually people start with larger values, and as they get closer to the peak, they make it smaller and smaller. Okay, so this is the steps that we do in gradient descent. So the gradient ascent, sorry. So what the algorithm looks like is that first at t0, we start with a value, initial value. It can be random. It can be an initial guess if you know something about W. And then we are going to repeat. We say t is t plus 1, and we say, okay, wt is equal to wt minus 1 plus new gradient of w at t minus 1. And we do this repetition until some stopping criterion happens. For example, one of the common ones is that until we see that really WT doesn't change much when we update it. Basically, when the gradient gets too small, that we don't see a big of a change in WT. So we can say WT minus WT minus 1. So the change that we are seeing, norm of the change is less than or equal to some small value epsilon. And that is the gradient descent algorithm for gradient ascent algorithm for finding the maximum value. And this is called batch gradient ascent. Why is it batch? Because we are calculating the gradients of W considering all data points in the data set.